All right, welcome back. We are INFR3110. That's in the fall 2020 semester at Ontario Tech University, and it's Game Engine Design and Implementation, Lecture 6, Part 1. And we're talking about game design patterns again today. It's something that I kind of did a little bit offline with you guys before the break. So here's where we're at. We're sitting at week 6, again, October 23rd. And we're supposed to have individual assignment number 1. Again, this is probably going to move to the tutorial side of the house next week. So expect it on the Wednesday that you'll get some kind of assignment that you'll have to do in day or in week. Again, I got to work out the details with Nicholas, but we're going to try and make it fair, something that you can use to practice some of the skills we've been talking about. Definitely, there'll probably be some kind of design pattern in there, because one of the things you're going to probably be asked to do in the final test is a design pattern, or at least draw it out or show it to me, talk about it, apply it, and all that kind of stuff. So I'm just going to bring up, before we start with this, I want to bring up some of the PowerPoints, and I want to talk about a little bit about what we had already done. So let's bring those up. So we had, wow, here's a bunch of them. And where to start. So here's kind of a list of all the PowerPoints that we've had so far in this course. I would start with solid principles when it comes to understanding design patterns. So if you look at this one, again, I'm just going to bring it up. I'm not going to go through all the details. It's for you to read, please. Think about it as homework. It's a little wordy, right? And I did it on purpose because I want you guys to have a reference so that you can look at these things. These are key, okay, these principles. So solid, single responsibility principle, open close principle, Liskov substitution, and so on. These are all, the reason why they're called solid is because we use them in software engineering, and each one of these principles, it doesn't matter whether you're doing a design pattern or whether you are design pattern for games or for software engineering or whatever you're doing. You should have these principles and others in mind when you're programming. Okay, so that's kind of where we go from there. So the question I have before we continue is, because I have an in-class exercise today that we have planned, is should we download the Unity version the GitHub project uses, or is it fine to update it to a new version? I think it's going to be fine, Roderick. You can update. So let's continue with the next part. So yeah, so solid is super important to understand. Again, I highly recommend you read through this, and I go through details. A lot of the examples you'll see it's my examples. Basically, these are little coding examples that I put up in Visual Studio 2019 and C++ for you. So they're all working examples. I've tested them all. So if you go through it all, it talks about what the single responsibility principle is, as an example, and what it means, and how it can be violated. But more or less, if you think about this at a high level, the single responsibility principle, or the S in solid, is that there should be one function. Things should, your functions in your classes more or less should be specialized. And when they are that way, then it becomes easier to test, and it becomes easier to understand what you're coding. So that's kind of the single responsibility principle at a very high level. Open close principle, the name is weird, but the idea is that we want to be able to not affect other classes. If you see what it says in here, it talks about how to do it, and then when we go in here, we go into the details about what this is about. So keep reading through it so you understand what each of these principles mean. They will be in some way on your final test. You'll be asked about something about the solid principles. So I think it's super important for you guys to understand what it means. Okay, so that, or what they mean. Okay. One thing that we haven't talked about, or a group of principles we haven't talked about, is the kind of the idea of dry, which is do not repeat yourself. So that's kind of another principle, if you will, of software engineering. Do not repeat yourself. If you see yourself repeating yourself in code, then there is a case for refactoring. You should refactor your code to make it something different. So again, I'm not going to go through these. Please make sure you look at them. I think it's important for you guys to understand. Okay, next. Then we talked about the factory method pattern. The factory method pattern I'm going to go over in code today, right? So And there's some nice pictures in here and stuff that I got from a textbook, which is really great. I think they're fantastic in terms of kind of making you understand what the factory is for. But think about the factory as producing a product. Every time we have the factory pattern, we're churning out some product. We're going to abstract away instantiation into the factory. So the factory does the instantiation for us. It does all the configuration for us, and then returns back objects that we need, right? So we can have multiple objects that I want to create. For example, bullets. It was the example that I used. Today's example will be tiles. So I'll show you, there's the factory pattern in Unity. I'll show you what that looks like in Unity. I'll show you the singleton pattern in Unity and a bunch of other ones. And how do they help us, right? So that's what these patterns are for. So again, the factory pattern is you abstract stuff. At the back, it's not just the factory pattern that you're getting here, but also the abstract factory. And there's a difference between the factory and abstract factory. The abstract factory, kind of creates families of products. So for example, chairs of different types, sofas, they're all sofas, but they have different shapes to them and so on, right? So product families as opposed to individual products. So that's kind of where the abstract factory goes in. Difference in C++ and C#. C# has the abstract keyword that we can use to identify that a class is abstract and that cannot create concrete objects. Okay, that kind of idea. So again, this is kind of key learnings for you. Factory is one of the most common design patterns that'll be out there, and it's important that you know how to use it. All right, so that's that one. Then there is command. And I talked about this before the break. I said command is probably one of the most difficult patterns to really understand how to use. It goes hand in hand nicely with observer. And we'll talk about the observer in more detail today because that's one that's slated for us to talk about. But the command pattern is really the idea for us to decouple our buttons and our user interfaces from our code. Instead of it being tightly coupled, and again, a lot of these patterns are like that. They want to decouple, and what I mean by that is take away the dependency for one thing pointing to another. Instead of having all the functionality hard-coded into a particular class, extract that. Make it so that other classes can use the same functionality, right? And the classic example for the command pattern, and you've used it already, is this idea of undo, redo, this kind of stuff that I've asked you guys to do in assignment 1 part 2. But also we have to also point out that there is this other part, which is if I want to do a remapping of buttons. So instead of my buttons being hard coded to a particular settings configuration, what if I want to, or you want to give your user a chance to, from an accessibility and usability perspective, you want to give them a chance to remap their buttons on their gamepad or whatever, what have you, or maybe you're making a strategy game or some kind of first-person shooter, whatever you're doing, you want your user to be more comfortable and so that they're used to using the controls that they like to use so that they can be successful. And that's part of what you're going to learn with HCI when you guys take that, which is the idea that you want to give the user a chance to play their own way. And I think that's a really great principle, right? So one of them that supports that principle is the command pattern. A little difficult to implement because in many ways it's like an event handler in some ways, right? That's what it's kind of like. So again, command really goes well with observer, which we're going to see. And you can see again, I've given you guys some C++ references, things that I've tested. Here is the command interface. In C++, this would what an interface would look like. In C#, you would have the interface keyword. And then this is what a command would look like. It is, yeah, Steph, it is. It's exactly what that combined command pattern combined with observer pattern is really an event system. That's what does it. You can make your own event system. You kind of need both pieces to make it work properly. And again, we'll talk about more of that. But again, this is some really good stuff. You can see that you'll have the idea of undo and redo and all that kind of stuff. And we use a queue, some kind of queue to be able to queue up the next command or go back to the previous command. Sometimes, again, we'll use multiple queues. We'll have the undo stack and the redo stack, and you can go back and forth and maintain state. That was kind of the exercise for your assignment 1, part 2. Okay, so that's command. And then that's in there. I think it's, again, an important one. Then the singleton. This is an easier one to kind of comprehend. It's like a global. That's what a singleton is. And the singleton really is the ability for us to do two things. One, provide a single point of access for a class. And two, there can only be one instance of that class. And the problem with that, the singleton right away creates a problem, and it violates the single responsibility principle, which we talked about earlier. Why? Because it solves two problems. Remember, single responsibility principle says, a pattern or a class or a function should serve one principle, not two. It's like serving two masters kind of thing in many ways. Maybe that's a bad example, but the idea here is that it only supposed to do one thing really, really well. And singleton does two things. And because it does two things, it creates a problem. One thing to remember is there can be only one, right? Which I agree with when it comes to the singleton. And one thing that each of these PowerPoints has that you can use, and I think it's useful, is a lot of these have UML diagrams. You'll be asked to make a UML diagram for sure in the final test. You will be asked to do it. So I mean, it's good to understand, to see them over and over again. I think it's important as well. So, so please take a look at this. And just when it comes to the way this is written, also remember that the underline, when you see something like this in a UML diagram, means static, right? So negative sign or a minus sign means private. So this is a private static instance. That's how you would read this thing, right? This is a public static instance or get instance method that returns the singleton. And here I've talked about a couple things if you haven't had a chance to look. One thing is the classic singleton and how it's not thread safe. This is, the negative about it. And then using magic statics, which I think is a way better way to go in C++. It is thread safe. And then how to templatize singletons. Imagine if I have a lot of singletons all over the place. I have a bunch of manager classes. And what I want to do then is use the same pattern, but instead of me having to, again, duplicate my code. Remember that other principle, dry, do not repeat yourself? Well, I'm repeating my code in template classes, or generics, as we like to call them in C#, will prevent some of that. It's not all of it, because if you notice, even in the final singleton, the manager singleton class that I created, we still got to do a couple funky things, like pass in the manager singletons class's reference into the singletons template, which is kind of a weird thing to look at. And we have to friend it and all this other stuff for it to work properly. But at the end, you get this single instance that it returns, and it'll prevent you from using the constructor function, which is pretty cool. So again, really great stuff, and singletons have a lot of use. One of the disadvantages of singletons are that they can be misused. And I talk about this in the example of advantages, global access point, and a single instance, and disadvantages. You can see there's a lot of disadvantages to use singletons. Some people really hate singletons because they can mask bad design, but we're going to use them today, right? And I'll show you where they can be used nicely. Okay, so that is the singleton design pattern. So these are the things that I'd like you to look at and be ready to discuss. For example, let's say in a short kind of discussion, whether it's a paper I'm going to ask you to write or something like that in the final test, where you're going to analyze some kind of scenario and you're going to say, okay, I want to probably use the singleton design pattern. I'm probably going to use the factory design pattern, or I might use a composite of these 4 design patterns in this particular scenario, Tom, kind of thing. And then, give me an example of what your UML diagram might be like. So there might be a little bit of writing in addition to some kind of development for your final test. But I'm going to remove the need for true-false multiple choice. I don't believe in that it works. I've tried it this week with, I will say, mixed results. And I find that, we have to try and find better evaluations for students, especially now in this remote COVID world, right? For now, until things get better. I just don't think they work properly. I think it just puts you under a lot of pressure and they don't give you a lot of value, right? So that's just me. And I always think that when I do an exam, whether I'm hosting an exam or doing an exam, there should be some learnings involved. And if there's not, and if it's just me just doing another evaluation, why bother, right? So it's not going to be like that. There's going to be something to learn. So what are we doing today? So last time we did the midterm. You guys did, for the most part, the stuff that I looked at fairly well. I think it was good. Well done. I also just talked about the design patterns I put up on Canvas for you to look at. Again, this is for your reference, and that's why I didn't go through it in a great amount of detail today. Because I think some of the PowerPoints speak for themselves. They're, again, very wordy. They're not something that I would want to show you in a presentation necessarily. And if I did, I'd probably skip through some of the stuff just similar to what I just did anyway, because no one wants to read walls of text. Okay, next is this week. What are we doing? Well, individual assignment 1 was due this week, so I kind of put it in there. But again, my thoughts are this is going to move, and I'll type it in there. This will move to the tutorial next week. That's the plan. And I'll say ... because I'm not sure. I got to talk to Nick and make sure he's okay with it. I don't want to pressure him either. And then today we're going to talk about 3 design patterns that need a little bit more discussion. And then we're going to try an in-class exercise today to get you guys going. So for the in-class exercise, like I said, if we go to Canvas, you can see that there is a GitHub repo for week 6 in-class exercise. Please go to that. And if you please download that ahead of time, like I said, for the people that were here earlier, it is a demo project that I want you to download. It's not huge, but it will take you a bit of time to load. And if you run it, and I'm just going to kind of do a preview of it right now. So let's just do it. So I'm going to go into, it's called, from my end, it's called procedural. That's what I called it, because that's what you're going to get out of it. And what I want you guys to do is improve it. That's the exercise today. So what does this thing come with? Well, if I press play, right, you're going to see how it dynamically or procedurally, if you will, if you want to say it's procedural, it procedurally creates your world. Okay? So that's what it's supposed to do. And notice that there's a tile count of 10,000 right now. Again, I coded this for you guys. You can see that it's quite large. If you press M, you'll see a mini map that comes up that gives you a little bit of direction on where you're going. So you can see as I come over to this like precipice here, right? There's a mini map. Another thing to do when you're doing this, if you press the backtick character anytime, it'll take you out of your app. So that's something that I've built in there as well. So you can escape just like you would when we were building things in C++. So, and if we go into if I split this with game and scene, let's just do one of these where I split it up. So you can see what it looks like on the right and on the left. And I'll just make this much smaller here so you can get a little bit more real estate. If I press play, then take a look on the left what's happening here. So it's trying very desperately to create the environment. And if it doesn't, it'll regenerate it for me. I'm also running the number of tiles that it's generating here as an example. It's running in a coroutine, and we'll talk about that a bit. And so, again, if I pull back, you can see the type of environment that it's created. Here's what it's made, randomness, right? And so it's kind of procedural. I don't know, Fletcher might disagree with me and say that it's not. It's more random than procedural. But there is a procedure, there is an algorithm that I used. It's just very simple. Okay, so that's kind of where this is made. And if I press R, anytime when I'm in the game, I press R, it'll regenerate my entire world again as best I can. And if it doesn't generate the tiles that I want, and I'll talk about that in a second, it'll keep regenerating them until I get to the threshold that I'm looking for. So here's an example of that. So that's not enough, but it'll try to do as many as it can. And if it can't, as an example, and the reason why it can't is because I prune any overlapping tiles. Anytime there's an overlapping tile, it'll remove it, right? So you can see now that it's going to happen, right? And you can see how it's growing very kind of organically as it's moving through. So that's kind of the way it's been done. So that's what you got that I gave you, right? And if you take a look here inside of the code, actually let's take a look at the hierarchy here up the top right. If you look at the hierarchy in your game controller, notice that the max tiles is there. Please don't put a crazy number in there. It will crash your system. This is not optimized. This is the exercise today. How can you optimize it? Can you find a way of making this better? which is which is the challenge today for bonus marks. Okay, so a couple things to note is I have maximum tiles and something called the threshold. And the threshold is actually the percentage, this is a normalized percentage of how many tiles are minimally will be acceptable before it tries to regenerate itself. So if I put 0.5, that means I want at least 50% of the maximum tiles that I put in here. So if it's 10,000, at least 5,000 tiles will be here, and unless I get 5,000 tiles, it'll regenerate it by itself. And you can delve into the code and figure things out. So let's put a bigger number in here and see what happens. If I go like 20,000, this is a lot. And by the way, I want you to think about what these tiles are. Each tile has it's really a block. Okay, that's what it is. If you want to see where the tiles are, and I'll explain more about the code later on, they're actually inside the resources folder, prefabs folder. And you can see the tile that I'm using right now is this one. Okay, it is a 10 by 10 by 10 tile, and it has a box collider built in. So think about the amount of the memory footprint we're talking about here. It's pretty big, right, from what I'm asking you to do. So now if I press play, and if I'm trying to do 20,000 tiles, it's not going to make it. And I got a pretty robust system. I'm running, remember what I said before? I'm running an i9 10900K, right? I'm overclocking at this point. I've got a RTX 2060 Super video card, not the best. I'm going to get my 3000 series when it becomes available. I've got 64 gigs of RAM, right? An M.2 drive for an SSD, which is pretty fast, right? I've got liquid cooling happening to keep everything good. It can run Crysis, it can, right? I know I'm flexing. I know. I'm not trying to say something, but think about this, and I'm still suffering, is what I'm trying to say. My system still suffers when it comes to procedurally generating or randomly generating this stuff. So if I'm suffering, and if you're running, let's say, the school laptop or something like that, wow, it might not even be able to do 10,000 tiles for you before it stops, right? So that's what I'm saying. So how can we optimize? Because we're going to think about a little bit of an optimization pattern today, right? So if I run this thing one more time, here's 20,000. Let's see what happens. I can also reduce the threshold to make it doable, but let's just keep it at the same threshold and then just run it, see what happens, right? So here you see it. I mean, I made it to 53 tiles and then it just stopped. Why? Because probably the tiles loop back on themselves and then they overlapped. And when they overlapped, I prune, and there you see how it's happening, and it's not good enough, right? So it's going to generate it again, and it's going to keep on doing it for a while until it finds its own, kind of the right number. And even it'll stop sometimes really low, like 4 tiles, 16 tiles, whatever. Why does this happen? Because the tiles are randomly going in different directions, and my procedure is, it can be improved, and this is something you can work on. Maybe you can improve the actual algorithm to make the procedural stuff work better. Maybe it's going to be using the flyweight pattern. That almost made it there, Okay, so you can see how that's working, and it didn't quite make it to 10,000 there, and you can see how it's going over and over again. So experiment with this thing. And then when you get it working, there's a further challenge to really push yourselves if you're interested. Okay, I'm going to put this out there to you. What if instead of, and I also have an enemy tile too that you can that'll come up almost like a tile to seek, right? So let's take a look here, right? If it actually makes it, and it may not, probably not going to make it. You can see that this made it to 5,000 before it reset. You can change the values, so you can wait longer before it tries again or whatever. There's lots of things you can do, right, to make it better. I'm just going to stop this now and not waste your time so you can try it. But what I want you to also think about is this. This tile that I'm using right now is a very basic tile. Okay, so if you make it work with this one, right, this threshold is for the percentage of the max tiles. So 50% as an example of the max tiles. I'm looking for, that would be the minimum threshold, so for me to stop generating. Otherwise, it'll keep trying to generate until it reaches the threshold. Okay? Because even if I put a number of 10,000, it may not make 10,000 because the way the tiles turn in on each other. And I'll talk about that a little bit later. But what if I, instead of having this tile be generated, I want to make it another type of tile. And let me show you this, because if I also made these tiles for you in Blender, like I talked about last time. So here's some tiles I made for you that are more complex. They have textures, they have a normal map on them, they have a bunch of stuff in here that is more challenging for this thing to create. Okay, so what if we swapped out the regular tile for one of these puppies? What happens then? And let me show you where that's done, so you know where it's done, so you can try it out. If you go inside the respawn, the tile factory. Here's the tile factory. Let's take a look at that in that file for a second while you're doing this thing. If I go to the tile factory and I bring up Visual Studio 2019, you can see that I'm looking inside prefabs tile. So this is the loading mechanism for loading a file that is a prefab without having a monobehavior class attached to an object. Okay, and I'll talk about all this stuff later on. Yeah, just double click on the Logan. Double click on the scene, because you're going to have to open up the scene that's active. If you look at scenes, and if you go inside the main scene, then it should work. Okay, so take a look at this. So what if I change this to, instead of tile, if I change this to tile 1? That is the one that is like way more, robust than what I tried before. Okay, so I'm going to save this, go back out to Unity here, and then I'm going to back out. And instead of, just to be safe, I'm going to just downgrade here. I'm going to go from 10,000 to something like, I don't know, 500. All right, and let's see what happens then when I do it. So if I press play now, I'm going to try and procedurally generate 500 of these massive tiles. Okay, and let's see if it even happens. Okay. And okay, so it's all going away, and it's going forever and ever and ever. It says tile count 1, right? And it's trying. It's really trying to do it, but the problem is it just can't. So can you make it generate at least 500 of these tiles? Let's go with a lower number. Let's go with something like 10 of these tiles, right? So see what happens then with this. And do they fall? Or is it something that, because remember, they don't have each of these tiles. And if I look at the prefabs tile 1, they have a mesh collider, right? But they're not supposed to fall, right? So if I run this thing, and if I say, okay, there's a lot less tiles now, right? And I want to generate a smaller amount. Well, I fall through, right? So what happened there? Can I not, put a tile in play? Let's take one of these tiles and put it in there. So let's just go into that tile. So if I double click, it'll take me into that tile, right? And if I look at the player spawn point, the player spawn point's like literally on top of the tile, right? So there's that player spawn point. And if I go to the player, here's where the player is. Right? And this is where, if I want to bring up the player also has, he's kind of inside, he's buried in here, so we can maybe put the tile in a different spot just for testing purposes. And again, this is just for you to try, right? And see if you can make it go. So there it is. So I'll put this tile in here somewhere so that the player can actually fall onto the tile and see what happens. Does this tile break, is what I'm asking. And it shouldn't. Let's see what happens if I did that. So here's where the tile is. I'm inside the tile, and it looks like parts of the tile are generating, but not all of it. So why is that? Is it because it's the tile map? Is it because I made a mistake? How can you fix this problem? Because it is a tile. Look, I just pulled it in here. So what is causing me to have this issue, right? So again, challenges for you guys. Some things. So your designer, the scenario is your designer's giving you some tools. They're not working, and he's asking you, or she's asking you to use these more complex tiles. Again, there's another one. Here's what the other one looks like. They're slightly different, each one of these. You could make your own maze with them all if you really want to. They are slightly different, every single one. Okay, here's the other one. Okay, so there's the 3 types. They're very similar, but they're the same shape or whatever, but they're different, right? And they all have a floor, and they all have buildings and everything else. You can see that they're all viable. They all have colliders and everything else, but somehow the factory can't do it. The factory can't create these things, and we'll talk about how to do that later. All right, and what the factory does. So that's your challenge for today. The challenge is, first, make your tile work So it works on your system. So you can try doing 20,000 tiles or 30,000 tiles or 50,000 tiles or whatever, right? That's the first challenge. And the second thing is, if you can make this work, then see if you can make these other tiles work too. By the way, if there's something broken and you want to try the original models, I've also included them, which is inside the models folder. So you can see the models folder are right here. You can actually look at all of them. And if you need to rejig the models from Blender, they're right here. Okay, so these are the ones that are inside the models folder. So everything is here for you if you want to explore this this package as we go forward. Okay, so that's what it's like. I'm just going to go back and put the script back the way it's supposed to be. So I'm going to go back to scripts, and I'm going to go back to our tile factory, and then put this back to tile. One other thing you can try, and I'd like to try and challenge yourselves this way as well. I'm just going to save this and go back out here. The other thing you can also try with the tile, if you look at the actual the tile itself in the prefabs, this one, the simple tile, which is the cube, you can always replace the mesh with the cube. So see this mesh right here? You can always replace it with something else, like, I don't know, a plane, right? And see what that looks like when you replace it with the plane and try and run this thing. So if I run this thing now and it's a plane, you're going to see that 10,000 tiles are even more difficult to accomplish with the plane because there's overlaps. And so what's going to happen is, if I said 10,000 tiles, it's not going to allow that to happen. So you can try smaller numbers up first, but if I go to the maximum tiles and I go 10,000 again, just like we were able to do no problem pretty much with blocks, but not so with flat tiles. If you notice, it'll have issues trying to do more than 1,000 or 2,000. It's going to be tough, and this one worked. That was good. Oh, but not quite. Look at that. It didn't quite make 5,000, the threshold. That one didn't even do more than 4 before it did it. So try it out. It's some neat stuff, but you can try different shapes out. And if you don't like, as an example, if you don't like the shape, right? As an example, like the this one might make it actually. Let's see. Oh, so close. If you don't like the planes, you can also try things like spheres, cylinders, and other kinds of shapes. Hell, you can even replace this tile with the mesh that I've given you from Blender if you really want to. So here's an example of that. So again, if I look at the tile itself inside Resources Prefab, and then I go into the plane mesh filter and I change this to something else. I can choose a prototype that I've given you. I've given you the standard assets in here as well. But let's suppose I choose, I don't know, cylinders. So I want to generate cylinders now instead of planes. Let's see what happens. So then I can do that, right? I can say, okay, give me cylinders. And then it'll give me cylinders. There we are, look. Right? And it actually did the cylinders. It's weird, and I can't move anywhere because the cylinders are so big. But you can change those things too. Oh, there's all those cylinders, right? You can change all those things too. Right now the scale is 10 by 10 by 10. Let's say I make it 2 by 2 by 2 for the cylinder, right? And if I did that and changed it, you can see here that I can have whatever crazy shapes I want. That didn't quite make it. And let me bring this over here so you can see them. So there it is. Oh, here's my enemy. He didn't quite make it in there. Okay, this might make it. All right, so there we go. So there's my shapes, and if I press M for my my mini map, right? And look, it's still struggling to do what I'm telling it to do, even with my system. So I press M. You can see this is a mini map, and you can see where I am. I'm kind of very small in the mini map, but that's kind of like cylinders, right? A bunch of cylinders that are procedurally generated here. And if I go to way over here and actually look at it on the editor, you can see that there's like a ton of tiles, right? And these were all cylinders. All right, so kind of cool. But let's say, for example, I want to make it so that I want to use the mesh. So I don't want to use this one, but I want to use these meshes. I can simply take other meshes here as well. Anything that's inside of your that's allowable will be here. All meshes that are here will be allowed, that you can kind of zero in on, right? So again, I'm going to go back to what it was. It was a cube, and it was 10 by 10 by 10, right? So you can always go back to what it was before. And heck, you even have the project online, so you can always go back there and check it out. You can change the material types. You can fool around with the colliders. You can do all kinds of stuff to optimize, but I'm looking forward to your solution. Okay? And you can see now that it's going to do blocks, right? So there we go. There's one thing to note is how it's being done, and I'll go through the details when we come to that point, and I'll explain this project in a lot more detail. Okay, for now though, I'm going to stop talking about this and let you play around with it as I'm doing my lecture, and then we'll get back to it. Okay? Cool. So that is the project that we're going to use for the in-class exercise today. All right, I'm just going to minimize this, and you can take a look at this, and we'll talk about how it's done. All right, so yeah. All right, so that's part of it. We're going to have an in-class exercise. Let's get into this stuff we're going to be talking about today, which is we're going to be talking about the flyweight pattern, and I'm hoping that this is going to help you, this idea of the flyweight. So it's a structural pattern, and we've talked about structural patterns before in the PowerPoints. One thing that makes the flyweight a little bit different than the other patterns is this idea of not just decoupling one class from the other, but actually removing parts of the flyweight, which might be helpful for what you're doing today. So the flyweight, also known as cache, I know they always come up with these little things, is a structural pattern that lets you fit more objects into the available amount of RAM by sharing common parts of state between multiple objects instead of keeping all the data in each object. So think about your tile. I have textures, I have a material, I have the collider, I have a bunch of things, the mesh. All those things are the exact same between one tile and another. What is different? I have the transform. The transform is going to be completely different from one tile to the other. The rest, it's all stuff that I'm going to be able to reuse, if you think about it, right? And in effect, I have to talk about this as well. We're looking at Unity. We're not doing C++. And in Unity, our idea of flyweights really are the prefabs. That's what they are. They are, in effect, kind of a flyweight. But we can make them even better, because if they were, then my performance would be like way better than what it is. Here's something also that you can try and do. We can also extrapolate or extract some of the common elements of game objects across C++ and have them natively managed, right? And perhaps maybe a faster environment than in C#, right? And that you might think that might be better. Sometimes it gives you better results, better performance than running strictly in C#. And we'll talk about that too. So storing something in some kind of file system, loading it up, and then after you're done loading the files, then what ends up happening is you get a better performance because you're preloading. All right, so what's the problem? So think about this. I want to make a realistic particle system or some kind of procedurally generated map, which is what I'm doing today. And, it works great on my computer, but it may not even work on your computer. Does anyone have a problem running this project on their computer? If you do, check mark in the participants panel. You can't run it. It just won't run. It's too slow. You can't do more than 500 tiles, something like that. Anybody? Again, remember, my specs might be a little bit more than yours, right? So, yeah. So you can't even run it, as an example. There'd be, so think about how do I optimize? Because it's got to run. It can't just run on a crazy gaming rig. It's got to be able to run when you make your game on every computer, right? Or the most of them, right? Anthony says it won't run because Unity won't open it. Did you try and upgrade it, Anthony? Is that the problem? Or is it some other problem that Roderick was mentioning before? Won't load layout. But you won't need it. Right? So you don't need a layout issue. Yeah. So we'll talk about I'll do that. What I'll do is I'll download it also, and then we'll fix it. Shouldn't be that way, but that's a weird thing that it's doing that for you, and it's not doing it for me. So this is part of the problem. The problem is we have this massive amount of data, and there's a lot of components of the data for each game object, as an example. And what's happening with the components is that there's some parts of the game object we can extract. Okay, so that's the problem. So after spending a bunch of hours and you figure out what the RAM is. So let's say, for example, this is a particle. Take a look at this. We have, and this is just an example online, but we have things like the particle itself, which is the game has an array of particles. We have an add particle method, right? And we draw on the canvas somewhere. In this case, it would be in our 3D space, right? Whenever we fire the bullet, it fires 1,000,000 particles. Here's 1,000,000 particles, right? So for a couple particles, no problem. But for 1,000,000, when you add all this stuff up, each of these things is bytes. But when we come down to the sprite itself, it's 20 kilobytes. And when we add all these things up, it's 21 kilobytes. That's what you have. Multiplied by 1,000,000, as an example, instances, works out to be 21 gigabytes. Okay? So that's pretty crazy, right? For just 1,000,000. And you might think that, wow, it's 1,000,000 particles, Tom. Yeah, it's 1,000,000. But you've played games, I'll tell you right now, that have 1,000,000 particles in them. Right, or something crazy, a crazy amount, but they've got optimizations. That's where it is. Okay. So that's how we kind of figure out the memory, and we'll talk about more about memory management as a memory management system later on this semester. Okay, so again, the problem is related to our particle system because of the way we do it. So what's the solution? Well, what we want to do is we have two parts, and this is what is going to be on your final test, guys. This idea of extrinsic state and intrinsic state. Okay, so what's the extrinsic state, right? Well, think about this: particle, the coordinates, the vector, the speed, things that are outside of the actual game object itself that you can set as a configurable object. How about intrinsic state or immutable stuff, things that never change? Your color, your sprite, your mesh, your model, your collider, all those things are things that are going to be common from one game object to the other, right? That's the intrinsic state. If we can extrapolate or extract, split the class into two parts, right? One part which is only extrinsic and the other one that's intrinsic, and then smash them together to make my particles later on, I have a win. I don't have to have all that data being used because I can point to, if I can point to the same pieces, then it might be easier for me to optimize. That's really weird. Last layout DLWT, eh? It's weird. I'm going to try that too. I want to see if I get the same problem when I download it. That's really weird. All right, so those are the two things we need to know. And the two keywords today are intrinsic and extrinsic, right? So extrinsic, you can think about it as being outside of the game object, so other configurations. And intrinsic are the things that are part of the basic, kind of like the immutable parts or the parts that we can point to inside of the game object itself. Example would be like, again, the model, the material, in 3D, the texture, all those things are things that we can reuse. Okay. All right. So here's what the flyweight would then do. When we separate it into two different parts, right? The particle itself, which is the intrinsic piece, right? The color, the sprite, all this kind of stuff. And then the moving particle piece, which is the coordinates, the vector, the speed, and the stuff that's extrinsic. If you separate these two things out, then what you have is you're only pointing to the things that you're going to reuse. I'm pointing to the texture, I'm pointing to the model, I'm pointing to all those things that I'm going to be re-instancing over and over again. So take a look at the RAM cost in this case. Again, this is theoretical. We have our color, which is 4 bytes, and our sprite, which is 20 kilobytes. That's not going to change. That's 21 kilobytes. But we're removing that piece because it's going to be reused. And notice that we only use it once. That's the red little bullet here, right? However, the other stuff, the coordinates, the vector, the speed, all this other stuff, that's 32 bytes. And if we multiply by 1,000,000, now we have 32 megabytes. Not a crazy amount of gigabytes, right? Which makes it totally doable if we were to use a flyweight instead of a regular game object. Again, this really works well in C++. In Unity, we have optimizations that do a lot of this for us. Okay. So part of the solution is this idea of of separation, right? So think about here Mario, right? Mario has, it's the same model, right? The exact same model. What is the difference? The colors, right? Otherwise, he's the same, right? Across different models. Same pose. You might have the same textures and all that kind of stuff, but the color, the tinting for each of the textures is slightly different. Okay? So we want to be able to store two things. The extrinsic state storage, which is the changing stuff, the transform, all the stuff that we can configure in the class itself. We want to literally separate the context class, which is the extrinsic class, right, from the actual game object itself, the intrinsic part. If we separate those two things out, then we can leverage reuse, which is what we want to go towards, right? So this is kind of where we want to go, right? So we want to be able to reuse the same particle over and over again. For every particle in these particles, then draw for the particle map, if you will, draw onto the canvas. That's what we're doing, okay? I'm just going to skip through this. A lot of times what really works well for flyweights is a factory pattern, right? Where I'm configuring the flyweight as an example. The thing that's left over, all right, the thing that's extrinsic, if you think about it, is the flyweight. That's why it's called flyweight, right? The lighter part is the thing that I want to instantiate, that part, right? The one that I want to point to is the intrinsic piece. That's the part that I only want to instantiate once and I want to point to. Examples would be things like using a texture manager, things like using a model, a mesh manager, where I load up a mesh as an example and I just point to it. So when I redo the vertices in the mesh, I'm just going to use the exact same verts. It's already been loaded. I'm not going to load it again, and I'm going to do it after I have the position, right? That's when I'm going to do it, not when. I'm not going to regenerate that stuff, right? That doesn't make any sense. So here's what the structure looks like. And again, one of the things that I've included in this, and the reason why I like these examples from the source that I got them from, I think it's a great source, is it gives you these little numbers. And I think it'll help you for your test too. So 1 and 2, so there's the flyweight, and this is the part that repeats, right? And then you got the context, which is the unique state, something that's going to change all the time. This, if you think about what the context is, and again, they switch around the words on me, but more or less the context is the part that is going to be extrinsic, right? The unique state. The repeating state is something that we want to be able to, kind of point to, which is what's happening with the context. The context is pointing to the flyweight itself, right? And it talks about that in the structure here. So the context class contains the extrinsic state. This one, the stuff that's outside of the flyweight, okay? All right, here's what UML. Here's another example with trees and forests. So you have a tree itself. Here's the tree. The tree has X and Y coordinates, and it kind of talks about a tree type. The tree type is the intrinsic state. The tree type, name, color, and texture. Those things aren't going to change, right? Whereas X, Y coordinates, the location of the tree, that's always going to be different, right? If I want to make a forest, I want to make an array of trees, right? But the tree itself is going to be pointing to the type, right? So type is a public reference variable that's pointing to this tree type over here, which is the interface, if you will. And we're going to use a tree factory to instantiate each tree for the forest. Okay, we're going to talk about the tree factory and how that works in a bit. Here's another example from the other source that we used before, where we have, here's bad stuff. You have, each tree they have the same mesh, they have the same bark, they have the same leaves, but the differences are the parameters, the positions. Maybe you have a tint that's slightly different or something else like that, but the rest are all the same. So what's the flyweight? The mesh, the bark, and the leaves. What's the extrinsic state or the context class? The parameters, the position, all that stuff is things that change. Anything that's changing is extrinsic. Anything that stays the same is intrinsic. And here's an example of how it would work visually. We'd have each of the trees point to the same model, which includes the mesh, bark, and leaves. Okay, flyweight. When do we use the flyweight? We use it when there's a huge number of objects which barely fit into available RAM. Example, our tiles thing today. Okay. How to implement? We divide fields of the class that will become a flyweight into two parts, the intrinsic state and the extrinsic state, right? And we leave the fields that represent the intrinsic state in the class. That would be the flyweight. And that's things that are never going to change. They're immutable. We leave them as constants, right? And we take the methods and the fields that are going to change and we put them into the context class, all right, which is another class. So you split the class in two, okay? And it talks about how to use that. Advantages, we can save a lot of RAM that has tons of similar objects. However, there's some disadvantages too. One of the things we do is we trade off RAM for CPU cycles. Why? Because at some point we're going to smash these two things together, right? At some point. So we may not have a lot of RAM, but CPU cycles are going to probably take a little bit of a hit. If you've got a machine like mine, it may not be a big deal, as an example. But and if there's some way, obviously, to offload some of this to the GPU, that might even be better. Instead of the RAM using all the cycles, the GPU would be the best way. Somehow, using GPU instancing will be a great way to do things with the flyweight. All right, so that is the flyweight pattern. Any questions around that for today? Okay, I'm just going to clear this up. Yes, it is. Scriptable objects is a great way of thinking about this, Matthew, right? Because it's exactly what it is, right? You've got two pieces, and then scriptable object is probably one of the best ways you can access objects, right? They're like static objects in some ways, scriptable objects, which are really cool. And I use them in an example I did last year with the game engines class, where we use the factory to create objects through the scriptable objects. This semester we're not doing that. We're doing something different. All right. Any other questions or comments before we move on? So I want to move on to object pools. So object pools is something we were going to talk about later on in the semester when it came to optimization. But if we're talking about flyweights, which is what we're talking about today, it makes sense that we combine flyweights with object pools. Okay, let's talk about that now. So I got a question coming from Daniel. It says, currently we have, how would we do this with tiles? Currently we have instantiating 10,000 objects. Will we instead be drawing the same object in multiple different positions? Yes, you could do that way. How about other things, other thoughts? How about separating out the collider as an example? And then, thinking about the generation process not including the collider. That might be a strategy as well. There's lots of little strategies, and we'll talk about it afterwards, Daniel. Hold tight, and we'll talk about some ways of doing things. Some things with code, some other things with configuration. All right, let's talk about this now. So optimization patterns. Again, desktop hardware is hugely improved, but there's still game performance problems with mobile devices and other type of handheld devices like the Switch. It doesn't have unlimited memory. Optimization is an art form, right? And some common design patterns we need to use to speed up the game. Object pools are one of those patterns, and what they help us do is reduce something called memory fragmentation. Okay, memory fragmentation is a bad thing. So here's an example that I pulled off the internet actually, which is pretty cool. You've got a ship that instantiates every bullet that comes out of it, right? And you might say this is okay, but actually what it does is there is a cost to instantiating, to creating a new bullet, and then destroying it at the end. And especially if I have tons of bullets over on the screen, you're going to see that it's far better for us to reuse objects in a pool of objects instead of instantiating every single time. The factory pattern, the way I've made the factory work right now, is I'm instantiating every single time. And this might be a way, again, of improving your performance. So I want 10,000 objects. Okay, make them. Give me 10,000 objects. Okay, now instead of me instantiating 10,000 objects on the fly in kind of a haphazard procedural way, why not just pull them from the pool? Okay, so I have a big pool of objects, right? And then I pre-allocate all of them, 10,000 of them, and then I pull them into my, to instantiate them afterwards. Or I just show them. Instead of me instantiating these objects, which takes up a lot of memory and a lot of instantiation happening all at the same time, I'm just going to show the objects later. And this might be an optimization we can use, and it works great with the flyweight pattern. Okay? So how does this work? So I fire a bullet, and then once it hits the screen, then what happens is it goes back into the pool. I have a pre-allocated pool of objects. Let's say, for example, I have 50 objects or 100 objects or 10,000 objects in a pool. And then I have these objects in my pool. That's fantastic. And what I want to do instead is I just want to request an object from the pool. Give me an object. Give me one of those tiles is what I'm going to say. Instead of, I want to instantiate them on the fly. So one of the biggest problems is this idea of fragmentation. All right. So what I mean by fragmentation is something like this. The heap is initially empty. This comes from our other source. I allocate some object, let's say as an example, right? So here's foo. I allocate the foo object, right? And then I allocate the bar object over here. And then I delete the foo object down here. And then I want to put another bar object in, but I only have this much memory. Guess what? I don't have enough space here or here. But if I was to move this memory over here, then I would have enough, right? Because I would have to make more memory or allocate more memory. So I'm going to have all these little spots. Not like I'm going to run out of memory, but what's going to happen is I'm going to have all these little pieces, fragmented areas of memory that I won't be able to use. That is the idea behind it, right? And what this does is actually compounds the problem that we talked about in the flyweight. It's not just about using the memory the way we did it, which is repeating a lot of the same stuff over and over again, but further to that, instantiating creates objects and then destroys the objects, and they don't get freed up in contiguous memory. That means there's little holes in our memory that we can't use. So we're not being optimal. Now, again, I want to frame this by saying that this would be the scenario if you and I were making a C++ game today, right? With no memory management. However, I also have to say that because we're running in Unity, because we're running in C#, C# has automatic garbage collection, and it has automatic memory management. And so one of the disadvantages of using the object pooling pattern is that what the thoughts are from different developers is that for the most part, C# can manage things well enough, modern languages, compared to C++, that we don't need to optimize this way. However, you're going to see that there is an optimization we're going to make today with the by using object pools. Okay, so cool. Let's go to this one. So what's the pattern look like? Well, what we want to do is define a pool class that maintains a collection of reusable objects. All right, so example would be game objects or prefabs. Each object supports an in-use query. I'm active or inactive. I'm alive or I'm dead. However it's going to work in your game. Okay? And when the pool is initialized, it creates an entire collection of objects up front, usually in the single contiguous allocation, like using a vector in C++. It'll actually contiguously, create memory or pre-allocate memory in your project, and then it's right next to each other. Each memory module is next to each other, which is really good from an access perspective. How does it look? So this is the diagram I drew. It kind of looks like this. This is how I would kind of classify it. You make an object pool. I recommend a queue. A queue always works best when it comes to C#. Even in C++, some kind of queue or a deck class, because there is no real queue necessarily in C++, you can use a deck class, which is a double-ended queue. And what you can do here is you can on-queue objects when you add things into the queue, and dequeue objects when you remove things from the queue. So when do I want to add things to the queue? When I'm building it. I build up a queue of game objects, right? As an example, I build up a huge amount of them. And what's the difference between a queue and a stack, guys? Again, we're talking algorithms now. You guys should know this. Who can answer difference between a queue and a stack? Is there a difference? How about that? FIFO versus LIFO. Wonderful answer. So first in, first out, right? That is the queue, right? So I'm queuing up, I'm in line, first come, first serve, first in, first out, the queue. Stack, last in, first out. I'm putting things on top of the stack. A stack of cards is a good example, a stack of plates, or a stack of procedure calls, the call stack, right? That is an example of LIFO, or last in, first out, okay? So here we're making a first in, first out. So I stack up a bunch of, or queue up, a bunch of bullets, or a bunch of tiles, or a bunch of particles, or whatever, and I keep them in the pool, right? I pre-allocate all this memory. Now, what I've done here in this particular thing when I drew this UML diagram was I made this diagram not only a object manager, but also a singleton. So this is an example of a singleton, right? Where I have a single instance of the object manager. And this makes sense because you don't want to have more than one bullet factory. You don't want to have more than one enemy manager, as an example, or whatever it's going to be that you're creating. You don't want more than one of those. You want one, right? Then you're going to use some kind of function like get object, or get bullet, or get tile, or whatever you want to call it. What's going to happen is it's going to return the game object from the pool. So you're going to dequeue the object from the queue. You're going to take it off the queue. So now there's less in there, less objects in the queue. When you return it out, it gets used in the game, and when it's done, it gets returned back into the queue at the back again, right? So you on-queue it again. So you dequeue it here, on-queue it here, and you keep doing that over and over again. And this is where you can use the objects again and again, right? There's also some utility functions that I made, a size function and is empty. For example, one of the challenges that we have with pools or object pools is what happens if your object pool gets emptied. Then you're going to run into an error. You're going to try and dequeue an object that doesn't exist, and you're going to run out. So there's two options here. There's actually three. One option is you say there's no more objects, wait, right? The second one is let's create a new one. Well, there's a demand for a new one. We don't want to create new objects because we're managing memory. But you know what? We've run into a place where there's a demand for a new object. You know, chances are if we create a new one, we may have less of a demand later. So let's make a new one. Okay, that's another strategy. Third one is I need another one. There's already one in play. Destroy the one that's in play and give me a new one. Give me that one back. I'm going to take the one that's already in play and get it out of there, right? So there's a few strategies here for how to deal with an empty pool, okay? Again, there's a few different objects here. There's the subject and there's the client. So think about the client here as the game controller class. The game controller class, it kind of sends a message to the object manager that says, okay, build me a pool of 50 objects, as an example. And it uses the init method to do that, right? So, hey, give me 50 objects. Okay, cool. I'm going to give you 50 objects. I'm building a pool with 50 objects. Thank you very much. Okay, great. Next, the subject is usually the enemy or the player or something that needs objects from the pool, right? So I say, hey, I want to fire a bullet. So sure, give me an object. All right, so it gives me an object from the pool. I'm able to fire that bullet off. Okay, cool. Then the game object has a role too. It's the reusable object that I'm going to put into the pool, but it has a role. It's going to return itself back into the pool. When it hits the, let's say for example, I'm firing a bullet, it hits the other enemy or a player. What's going to happen is it's going to say, okay, I'm dead. I don't need to be in play anymore. Take me out and put me back into the pool. That's what the game object will do. So each piece here has a role. And that is high level of a way to do an object pool. We're going to actually code it today together. All right. So, and I've given you details on how to do that, like a step-by-step. Create an object pool, create a static function, create an init function, and so on. All right. When do you use it? You use a pool when you need to frequently create and destroy objects. Okay? And objects are all similar in size. Right? That's an important thing. Allocating objects on the heap is slow or could lead to memory fragmentation. These are good reasons why you want to do it. Each object encapsulates a resource such as a database or network connection that is expensive to acquire and can be reused somewhere else. Okay, so these are really good reasons to use a bullet pool or some kind of object pool. Advantages. It offers us a significant performance boost, and I like to say it like this sometimes. Even if I load up a bunch of memory, let's say for example I need 16 gigs of memory to run my game, let's just say. And it's almost at the limit of what I can do. Or let's say I need 10 gigs of memory, right? If I'm pre-allocating, right? Where if I don't pre-allocate, I can start with a lower amount. If I start with a lower amount of memory and then I go into a scene where I need a lot of objects happening all at the same time, I'm going to have inconsistent gameplay, my friends, which is bad. I don't want inconsistent gameplay. What I'd rather have is consistently bad gameplay compared to inconsistent up and down gameplay. And I mean consistently bad as in the same amount, the same level of gameplay. In terms of frames per second, in terms of interaction with the environment, everything. Okay? So that's what it can do for us. The pool object is obtained in a predictable time. So it's not going to be random. I'm not going to just create new objects when in a random time. I'm going to get them all at once. It works great with the flyweight pattern, which avoids duplicate memory usage by using the same object in multiple contexts. Okay? So this is great. And finally, the disadvantages, there's a few there too. Unused objects will remain in memory. So let's suppose I don't need all the tiles. What if I allocate 10,000 tiles, but my procedural algorithm that I'm using to create this organic looking map, what if I prune 6,000 of those tiles and I only need 4,000 of them? Well, guess what? Those tiles that are quote unquote pruned are still in memory inside my pool. And so we can call these object cesspools as opposed to object pools, which is actually an anti-pattern. So we don't want that either. If we don't need all the objects in the pool, they should be purged. That's how we should do them. But if you purge them, then it kind of takes away the need for the pool in the first place. Okay. Here's another one. Layering on an already managed memory system. For example, we talked about this. C# is a modern language. It has, garbage collection, all this kind of stuff. And in Unity, we have something called high performance C#, right? Which is even more optimized than regular C# that you would have, specifically for Unity as a scripting engine. Unpredictable object states. So you can't tell, as an example, if objects are alive or dead, right? They're going to be alive or dead according to the algorithm that you state inside of the object itself, which you don't know when they're going to disappear, as an example, not exactly, and you don't know exactly when they're going to appear in state again, in an active state. And of course, there's the last one, like always, for any of these patterns, which is increased code complexity. Why? Because we have all these other pieces all over the place that we want to do. The same thing with the flyweight pattern and all patterns. Really, you have a bit of an increased complexity. But the great thing about them is they give you something in return for using them. Okay. All right. So I've talked for about an hour and 20. I think this is a great place to take a short break. But before we do that, let us talk about the little in-class exercise that I want you guys to do. So let's do a little bit of inspection of our little thing today. So some people have had some issues with the project. They've been mentioning here up on chat, and I know that you guys have been experiencing some layout issues. It could be because I might have a layout that you don't have. It could be a bug that you're talking about. Really what I'm doing here is I'm using something called a 2x3 or tall layout. It's a tall layout. So if I go to tall layout, it looks almost identical to what I had before, like this. Okay? This is my tall layout. And all I'm doing is I'm actually layering on top of my tall layout. One thing I'm doing is I'm reducing my the assets here, so it looks like this. It can happen regardless of the project. I know it's kind of a weird thing. It's also maybe my version of Unity 2020 compared to yours. There's so many things that can happen, right? The rigid body first controller, that's really weird. All right, that is really, really weird. So you should have that in there because I've actually added in as a standard asset, right? So standard assets has the rigid body first controller. That's right here. So if under character controllers, there is first person character controllers. Under prefabs, you should have both of these, right? So worst case, what I'll really do, so layout issue that I had open 5 minutes ago. So Daniel, are you working now? Sorry, I just want to make sure you're up and running. If worst case scenario, guys, if it continues to fail, I'll just put it up somewhere on a Google Drive where you can just download it. That'll save us a whole pile of time. I know that sometimes it happens with Unity, and I do apologize. It is what it is. If you can't make it work, I'll open up a Google Drive, I'll put it up there, and then will get you going. All right, so let's take a look at this crazy piece of code that I've written. This monster of a code, right? So a couple things to go through. Let's look at the project. One, if I look inside my scenes, I have something called the main scene. Okay, main scene, and the main scene itself has this scene right here with a bunch of extra things like lighting and a bunch of other stuff. Okay. Under scripts, I have a few scripts. One of them is the game controller script. Let's look there in the game controller first. So what is this crazy game controller we speak of, right? Well, it does a couple things. It uses a header that says tile layout, and it has things like the threshold and maximum tiles, right? The way it works is it talks to the, here's the list of game objects. The list of game objects is something we can use, but what's happening here is this list of game objects is happening after the fact. I'm actually loading up the list of game objects after. That's what's happening afterwards. I have a couple of keys that I listen to. So the way I do the add tile is I kind of check to see if my tile position, and if you look what tile position is, it's a dictionary of strings and booleans that basically keep track of if I have the same location used twice. So what I'm doing is I'm creating a key value, string key, that takes the location on the X, Y, and Z axis and creates a new key value. If that key value already exists, it means that that exact location is being used. And if it's already being used, skip. I don't want to put another tile in there, which means that if I call add tile as an example, when I call add tile, what's really happening is there could be some pruning right here that's happening. I'm not going to instance anything until as an example, until I'm ready. The other thing is this. I'm going to use the tile factory. I do have a tile factory, and notice it's using instance, which means the tile factory itself is a singleton. Let's get in there for a second. So if I go to tile factory, so go to definition, here's the tile factory. The tile factory has tiles, the tile itself, a game controller, reference to the game controller, and something called an instance. The instance is a static instance which starts off at null. Now, by the way, I have to tell you that this version of the singleton pattern that I'm using is not thread safe. If you wanted to, we would rejig this version of the singleton pattern so it would be thread safe. And the way to do that, of course, is to make a private static instance that generates the instance right away, as opposed to doing it this way. Okay, the instance itself just returns this. That's how it would look, which is different than what we're doing here. Okay. However, for our examples, this is more demonstrative, which means you can see what's happening here, as opposed to it being in a pattern that's a little bit more cryptic. Okay. So what's happening is when the tile factory the instance is called, it creates a new tile factor, or it accesses the tile factory constructor, which calls the start method. The start method loads up the prefab from the resources folder. That's what it does. And it also gets a reference to the game controller object in the hierarchy. That's the two things that it does. All right, so it gives me the tile prefab. Hey, tile prefab, thank you for, I know where you are now. And then what I want to do is, as soon as it calls start, right, I haven't really done anything yet until the create tile method is called. So example, I would go through this. I would say, hey, instance, hey, tile factory, instance. The instance, if you think about it, is your gateway to the entire class. Hey, instance, I want you to create a tile. What does create tile do? I pass it a location where I want the tile to be created, right? I use instantiate here, right, in my factory to create a single tile, the one that I loaded. Now you can change this create tile method so it can load different kinds of tiles, and we'll do that later on, where I take the parent, the transform of my new tile, and I set it to the transform, the transform of my game controller, which means when I run it, and if I look at my main, if I run this thing now, let's make the 10,000 tile thing happening. Take a look at game controller, what's going to happen. I get all these tiles that kind of appear inside of game controller, so it doesn't pollute my hierarchy. That's what's happening here. Okay. So this worked, right? As an example, here I am, and you can see that I can look around and whatever. I did have a bit of a memory lag though, and you can see that it randomly generated my scenery, which is kind of nice. It worked out. I can use M, right, to have my little mini map pop up, which is just an additional camera that's attached to the player object. Okay. The camera that's attached to the player object, I'm just going to go into diverge a little bit here. Here's the mini-map camera, right? It looks at a couple things. It's an orthographic camera instead of a perspective type of camera, right? And it can only see player markers, and it can only see the actual scene itself, the tiles. It cannot see other parts of the scene. I've basically said that from a culling mask perspective, it doesn't see the enemy, but it can see markers. Okay, and you can turn off the rest if you want to. All right, cool. So that's the mini-map. The mini-map actually uses a render texture. A render texture is an object that's going to be where the camera is rendering to. The render texture is inside of textures. You can see it here. You can see that the mini-map render texture is right here. If I click onto it, it'll tell you how big the size of the mini-map is and how it works. Okay, you can actually change this and optimize it if you want. Notice that there is something called dynamic scaling, and I haven't turned that on. I also have a couple of markers. I have the player marker, which is just this that I drew, as well as the enemy marker, which is identical but red. Okay, so I have the player marker and the enemy marker. I also have different textures for the ground, all right, that I downloaded from textures.com, as well as the concrete wall and the roof tiles. Here's the roof tiles that I use, right? So you can, and then I've also created normal maps for the ground, the wall, and the roof. So those are the normal maps that have been created through Unity. Nice, 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 right? And I have materials. All these materials, this is the ground material that's being used right now for the standard tiles. This is the ground material that's being used for the more advanced tiles, if you can get to work, make them work, the roof tiles and the wall tiles. Okay, so that's the materials. And again, you can always change the type, the preview here with what they'll look like when they come into play. All right, so that's the materials. The models include all the models from Blender. So these are all the models. You can actually kind of look through what they would look like, right, in Blender, right, or from Blender. You can look at them right here, right? They're very, very simple. They're not very complex in any way, but they include colliders. And if you notice how this is done, if you look at tile and if you look at model, I already have this thing that says generate colliders. So colliders are automatically generated for the model, which should give us a convex collider for each of the models. So that's how it works. That's done. Okay. Just going through it so you understand what's inside the code. I have a depth plane. The depth plane is invisible, and it's 500 meters by 500 meters. So it'll cover most of the map. Chances are it's going to hit the map. And why do I need the depth plane? Well, what if my enemy or my player hits the depth plane? Then it'll go back to the respawn point automatically. That's how I do it. The player is actually using a character controller, and I turn off the character controller in order for me to move my player to the spawn point, and then I turn it back on again. Otherwise, I cannot affect the player's transform. Okay, so that's kind of how it works. In terms of our structure. Okay. In the canvas, this is where I have the mini-map. The mini-map is actually, and if I double click onto it, you can see how, I got another joiner. We can see how if I look at the canvas in 2D, that this is what it would look like. I have the tile count, which you can turn off if you want. I have the mini-map, which will appear here on the top right corner of the screen, as well as kind of like little message says press M to toggle the mini-map. So that is the mini-map itself, and there's a bunch of other stuff here that you can see. Okay, so that's kind of the structure. It's not very complex. Let's go back to the scripts. I'm just going to undo the 2D thing. Let's go back to the scripts for 1 sec. So that is your game controller and your tile factory. Okay, what about duplicate? Duplicate is actually the script that I use for each of my tiles. When a tile comes into existence, it duplicates itself. this is what it does. So this is how the procedural part works. I generate a random number between 1 and 3 tiles. So I have up to 3 tiles, right? And then what I do is I say, okay, cool. Let's run through a couple of scenarios, right? I'm going to, for every tile in random tiles, so let's say if I got 3 tiles, I'm going to start off with my random direction as 0, right? And then I'm going to generate a range of possibilities. So 99% of the time, okay, I'm going to say that there's only going to be a random range between 0 and 4, which means that mostly it's going to be a flat area. Why? Because the direction is based on back, forward, left, and right. This is how I kind of did it. I said that between 0 and 4 is just a flat plane. 99% of the time. Now, if I have 100,000 tiles or 10,000 tiles, I'm going to hit some up and down directions, as you saw, right? 1% of the time, so if it's, let's say, if it hits me inside the 1% of the time, I'm going to have some tiles that are up, above, or below me. You can change these numbers, and you can bring them forward if you want to. So you can mess with this percentage. So instead of saying, I don't know, my random direction probability is 99% being flat, well, you can make this so it's 50-50, which means you'll have some flat areas and a lot more, mountainous kind of areas if you really want to. Okay, here's something that I look at. If my tile position is already something that I already have, then continue. So prune. I prune again there. So I don't let the tiles overlap each other. I do it twice. I prune at the beginning and I prune again at the end when I do my random direction. And then what I'm doing is, if it passes through here, then I'm going to add my tile. So this is where I'm going to add a new tile, potentially. That's what I'm going to do. So first of all, I prune here to make sure that I'm not generating 3 tiles that are the same. So I'm generating from 1 to 3. What if I said each one of them is forward? Well, that would be bad, and I would automatically prune those before it even got to making the tile. So each tile actually generates itself. Okay, I want you to think about this for a second. Nothing is wrong with doing it this way, but there are optimizations that could be made. That's all I'm saying, right? This is just one possible way of doing it. So that is the duplicate script. All right, almost done. Then I'll let you guys go and do your thing. The direction is just an enum. That's all it is, an enumeration that tells me right, left, forward, back, up, and down. Okay, that's what that is. And respawn player basically is just a little script that respawns the player. You can probably prune this stuff because start and update can be deleted, although there's only one of them. It's not that much of a hit. But all it does is basically say if it's the player or if it's the enemy, if they hit the death plane, then what's going to happen is, because this is respawn player is actually on the death plane, if it hits the death plane, then they go back to the respawn points. That's what these things do. Okay. There's some other code in here too, but for the most part, this is it. All right. So, challenge for you today. Take the code that I've given you, and hopefully all of you can run it now at this point. You've kind of gone through the fixes and everything else. And and then see if you can optimize. See if you can either extract certain parts of it to create your flyweight pattern. That might be something you want to try. You can do this in groups, guys. You don't have to do it as singles. You can get together with a partner to submit your in-class exercise, although I do recommend trying it on your own as an example. Right, so that's one thing you can do. You can create a pool, an object pool, which I don't really do here. I'm keeping track of objects, but I'm not pre-allocating objects. So what's happening right now is each of the duplicates, the way I'm doing it is when an object is instantiated, then it duplicates itself. It clones itself, right? There's other ways to do this. And notice also that it does it inside of something called a coroutine. So the generate random tiles method is in a coroutine. And so what happens is it'll run in a different thread. Okay? Again, be aware of what's happening here if it's running in a different thread. Okay? So lots of stuff going on. All right, and then let's see if you guys can get better performance than I've given you. And if you do, what I want you to do to make this happen is let's talk about it today. Talk about a little bit, like do it in class. Talk to me about it and say, and I'll try it online live after the break. Okay, so let's take a short break. I'm going to stop recording now. I'm going to give you guys, let's say 20 minutes. So we'll get back together at 4 o'clock and see what you guys got. Okay, and then we'll go from there. We'll do it together as a group. Okay, I'm going to stop recording now.